嗯，应该可以，我把这个键连上了。
嗯，对，右边。
录制。
它好像进去是自动
OK，
谢谢。
然后就是，哎，这是啥？哦，待会就是看一下。
Okay, good morning, everyone. Thanks for your patience to wait for us to set up the computer. Because it's a little bit complicated. We have a web camera here to capture the face, and we also use our own laptop. We did install some driver for using the webcam. So finally, thank you everyone for coming to this tutorial. Today, we are going to present the topic about the federated intelligence in web. And this talk will be jointly delivered by me and my colleague Peng Yan and Shenchao Chen. My name is Guo Donglong. I come from the Australian AI Institute. This is part of the University of Technology Sydney in Australia. By the way, the overall agenda is look like. Should I use that or hello? Yeah, maybe I don't need to use that. Hello. Okay. Do you think I need to use that or no? Yeah. So the overall agenda is look like we will have a introduction of this new idea about federated intelligence that cost about 30 minutes. And then I will give a brief conceptual framework of the federated intelligence that's from a learning perspective that we are using another 60 minutes. Then we have a 30 minutes coffee break. And when we come back, Peng Yan, we are talking about the federated intelligence with agents in 40 minutes. And Shenchao, we are talking about the application and the open challenges. At the end, we will have question answering. But feel free to chat with us in the coffee break or after the presentation. Now we move to the part one, the concept of federated intelligence. That includes three subdomains. The first one is about the motivation, why we need to have federated intelligence. The second one is about the foundation of the settings, learning on the federated settings. The third one is the conceptual framework of this idea. Now, we all know the web actually is connect everything, connect everyone in a kind of information systems, include hardware and software. And it was first designed to share the documents. So basically it's designed for the hypertext. But now the web actually is evolved to a large infrastructure. Every day there is a lot of data was generated by the human, by the sensors. So I do remember in 2010, an idea about big data is proposed because there's too much data generated from the web. So they proposed the big data idea and they proposed that as a new challenge for the data processing and also for the data-driven AI methodology. And there's another new trend is although the cloud service is the mainstream architecture to provide the web service, but they still have a new trend to push the data processing and also a lot of service to the on device, because the on device have a better real-time response and they can work offline and also they can have a better privacy protection. So also for the smartphone, because they improved hardware computational capability, the on-device application and also the hardware configuration of the smartphone become feasible to conduct this kind of on-device service. As we mentioned, the World Wide Web is actually simply designed for translate or sharing the text data. But now the modern web is evolved to a completely new systems, a new ecosystem. For example, there's large-scale real-time engagement with the users. So including to provide the video, short video, and the user also can communicate to each other via the social networks and also professional networks. A lot of people also spend lots of time on playing online game and use other web service to facilitate their daily life. And most of people actually stay connected all the day because we have smartphone. A lot of people spend more than 5 hours a day on the smartphone. And the widely used of Internet of Things to make a lot of sensor data be collected and then also be uploaded to the web. Then make the web data is more diverse and more huge. And from the technology perspective, there's a lot of more and more data-driven and AI-powered automation tools to be applied to process this data and also to provide the automation service for large-scale end users. There is also a lot of challenge, or the essential challenge of the web is actually information explosion. At the early stage, the information retrieval can solve that exploration in a nice way, like Google did. And then as time going, the recommendation become another way to solve or to reduce the risk of information explosion, because giving millions of video, the user cannot choose or cannot make a right decision which one is actually they want to watch. But recently, the large language models combined with the information retrieval or the search engine that become a new way to further solve the information explosion problem. So that is the overall of the World Web looks like at current. Based on that, the web intelligence is a subdomain of that. Is actually focused on to using the artificial intelligence tools to solve the to provide or design the new product for the web, and also to process the large-scale data collected from the web. If you look at the left side, the left picture, that is the research track that from the cover paper in this year. This gives a basic understanding of the overall picture the web technology community actually focus on. So it have about the online marketing, that is actually the advertisement of the internet company. And the second one is the graph modeling. That is to model the structured data in the web. The third one is about the responsible web. That is called to make sure everyone using the web properly. The fourth one is the search and the retrieval related AI technology that used to solve the information exploration problem. And the fifth one is the security and the privacy issues that that is also a important problem of web. The following one is the semantic and the knowledge that actually is trying to learn or understand the semantic knowledge of the text on the other web data. For the social network and the social media, a lot of people are using that, and so it's also a quite important topic of the web community. We also have focus about the system and the infrastructure of the web, and the Internet of Things. That is also the infrastructure and the important problem. And the last one is about the recommendations. So how to modeling the user personalization and also provide the recommendation to the web users. So actually, all of these have all of these problems are highly engaged with the artificial intelligence technology. Also, we didn't put a separate track about the AI tools on web. Actually, all the web tracks have components of using AI technology on these tracks or solve the problem on these tracks. Now, so this is the overall picture of the web technology community. So we are talking about the recent trends of the web technology, because I would say from 2023, the most excited technology is large language model. It starts from 2023. Actually have proposed a significant impact to the web and to a lot of domain. So make us to rethink about what the future web should look like, and what's the new challenge if the web meets with large language model. Okay, a large language model, I assume everybody know very well, and there's lots of introduction of large language model. Here give a very brief introduction. Is the current large language model comes from the I would say it starts from the attention mechanism. That is the new neural architecture compared to the convolutional neural network and the recurrent neural networks. The attention mechanism is more I would say it works perfectly with the GPU, with the hardware. So for the convolutional and the neural network and the recurrent neural network, that was designed in the CPU intensive computation. But the attention is designed for the GPU that is have more focus on the parallel computation. So based on the attention, the transformer architecture was proposed. That is a layer-wise the self-attention mechanism and in a encoder-decoder structure. And that was further improved in pure encoder structures. And then there's lots of the move to the large language models. As we can see, there's in this technology line, there's a lot of large language model have been developed. Also, some of them performs very well, but most of the high-tech company will have their own large language model. Part of them are training from scratch. Another one, maybe part of them are based on the open source and then fine-tuned based on their own data set or their business. And some of them can be open source combined with the destination of other large language models. So there are different large language models available. So when we think about the web with large language model, because we can think about large language model is a kind of infrastructure, then this could be a core technology deployed on the cloud servers. Then it can provide the service to the end user in a large scale, and also, for example, the customer service. They can provide the customer service and using the language as interaction tools. So that is the way to think about, and I think this is also the current way to provide the service by combining large language model and the cloud service. And another way is large language model as a participant, because everyone are using the large language model to help them to process some tasks. So there are more and more large language model generated contents, and this will become I would say this is a dominated information source of the web in the future. Think about this way, about 5 or 10 years later, there's most of the web information source actually is generated by a large language model with human inputs. So this will be an interesting scenario for the future. The third one is because the web, we can provide the data like for the recommendation and for the video and for the social networks. So how about we think about other foundation model that could handle this kind of data, because the large language model only focus on the natural language. So how about the video? How about the time series data? How about the social network data? So the large language model can co-work with other models to jointly provide a more comprehensive service to the end users. So based on this idea, we are thinking about what the future of the web looks like. We would say, okay, possibly everyone will communicate to each other through a large language model powered virtual assistants. For example, because in most of the time we are communicating to each other, we need to introduce a lot of background information and then make sure the other person can understand the background and get the profile information and then can get the point. But how about the virtual assistant powered by the large language model? Then they can use your private information and also get your history track record, and it could be deployed on your smartphone. then they can get the data from different apps. And after that, they can communicate with another large language model on this cloud service. For example, you want to have asking for the customer service from a bank, then the virtual assistant on your smartphone can communicate with the large language model on the bank's server. They can communicate to each other without you to waiting for answer the question. Most of us actually have, I would say, they have not happy experience about the customer service with the bank or with other public service, because there's too every time when you're calling for the customer service, you have to waiting for a long period. You need to pick up the when you're calling the phone, you need to pick up different options to direct you to the right service branch of that company or the government agency. But this takes a long time, and it's also very annoying when you have to waiting for 1 hour to have a customer service available. So if you have a virtual assistant can help you to communicate with them, then you don't need to spend time to worry about the customer service. So for example, when you are eating breakfast, you want to talk to your bank about what the home loan of your bank. Then you just send a command to the virtual assistant. Then they can collect all the information and talk to the bank directly. And then you don't need to worry about that, because to my knowledge, the current managed system of the society is quite complicated. So every time you communicate with someone or with some organization, they are asking a lot of information. So that is an urgent need. We have a virtual assistant to help us to do I would say this is kind of paperwork or the basic information filling of the form with the hospital, with the bank, with the government agency. Then that can save us time to focus on more important tasks. So if we are targeting to that direction or to targeting to that future, what should it be looks like, or what's the fundamental challenge? So this challenge should be how to ensure the efficient learning and communication among, I would say there's millions of or billions of customized lightweight large language model. There are not one large language model on the cloud server. There are a lot of lightweight large language model on your smartphone or on your computer or on your Tesla self-driving car. So that could be the future should look like. And so how to solve that problem, or how to how can we prepare for that future? Maybe in 10 years time. It's not about 1 year or 2 years. I think this will come after 10 years. Okay, here we move to the foundation model because I would try to give a quick definition of the foundation model. Foundation model actually is a machine learning terminology that is similar to the large language model, but is more focused on a more broad aspect of different machine learning tasks. Compared to the traditional machine learning models, the traditional machine learning, normally each model are designed for a specific task, but the foundation model actually is designed for a broad range of tasks in one domain. So you don't need develop hundreds or thousands of different machine learning models to solve different tasks. You just need one foundation model to solve solve a large number of tasks in the same domain. So normally to training the foundation model, it requires a lot of training data, and the scale of the parameters of foundation model is quite large. So that giving them powerful capability to understand the complicated scenario of a domain, and also capable to catch the complicated relationship of of different random variable in a particular domain. Large language model is a type of foundation model that focuses on the natural language processing related tasks. So if we get back to our predicted future of the web, so if we expand this from large language model to foundation model, so our virtual assistance is it could be majorly supported by large language model, but it also have another tools that can manipulate it or operate it to understand other source of data. They could understand the video and the visual input, or they can understand the time series data maybe comes from your smart device to monitor your heartbeat and your daily activity. So all this kind of information, we need a different type of foundation model to process for different domain. So in the future, we will think about they have you can think of have a virtual assistant that's a kind of AI agent, and you have different foundation model. One foundation model could process the natural language model, and the one foundation model to process the time series data, and the one to process other database input, and the one foundation model for to process the visual input. And of course, you can also have a kind of the agent can also have a particular tools to merge different foundation model to provide the multimodality processing. That could be another way to combine them together. So no matter what that looks like, and the fundamental challenge, so we need to rethink the current machine learning paradigm from one model centric to a large scale or maybe millions of model focus. So this is not a problem for training one model. We are focused on how to training millions of model, and so that will be, I would say, this is a different learning paradigm. So we need to this is quite a challenging task. I wouldn't say because the traditional machine learning, we normally think about if solving one task is easier because you just learning the probability by using the parameter, the model parameters, trying to approximate hidden distributions. But if you think about millions of models, so each one have different objectives, they could be slightly different and also have some part of to share. So this will be a challenge scenario, and also need a new, I would say, need a new machine learning theory to support that kind of tasks. And also there's some basic exploration on this direction, but still quite in the early stage. So we are moving to the second one. Yeah, a quick recap is about the motivation. Yeah, the web is evolving, and we predict the future of the web should have combined with more large language models, and then we can have more AI agents to help us to communicate to each other. So based on that predict future, we propose the challenges that the future we need to have more customized AI models that are deployed on your personal devices. Okay, that is about the future, and then we move back to the foundation that learning on the federated settings. Federated learning actually was proposed in Google in 2016, so it's quite 8 or 9 years ago. It was first proposed also proposed by Google for the Android systems, because every time you type in some words in your smartphone, they need automatically predict what the next word you will type in. Then they can automatically complete the typing for you, then save your typing time. But if if every time you type in some words, you need to connect with the cloud server, of course, that costs a lot of communication and also costs latency between the response. So every time you type one word, it's waiting for 2 seconds to get the recommendation. It of course doesn't work. So they want to deploy that intelligent model to the smartphone, then make sure they can working on devices rather than every time contact with the cloud server. So this is the motivation of federated learning firstly proposed by Google. And similar technology have also implemented in Apple, the Siri. If every time you use Siri to send the command, and the Siri also need to train to understand and recognize your voice, then they have a small intelligent model deployed on the smartphone. So this is also supported by federated learning. They don't need to collect your voice data onto the server. They can tune in existing model to understand or recognize your voice on the smartphone. So here, give the definition of federated learning is actually a machine learning setting, and they have multiple entity collaborative solving a problem. And it usually have a central server to coordinate that learning process. And the important thing is each client raw data is stored locally, then don't need to collect your data to the servers. Then you can run the model and store the data on the smartphone and run the model and train the model on the smartphone. They don't need to exchange the raw data, so that could be a way to protect the privacy. And all you need to do is upload the changes of the learning parameters. So the parameter will be aggregated at the server, not the raw data. Here is the evolving of machine learning paradigm, and the first one is actually centralized machine learning. That is the classic one. The central server collect all the data and stored on the server, and then use this data to train the model. Actually, most of existing internet company actually doing this way. They can collect all your behavior and the watching history, and then make a very accurate advertisement recommendation. And that is the core business they are making that. So sometimes when you watching something and then advertisement will come to you in a very accurate manner. So because they actually collect all your data and make the recommendations quickly and in real time. Another machine learning methodology is distributed machine learning. That is it would be distributed computing and put the model and the data sets into different server and then combine it back to the central server. That is kind of reduce the computation workload. And this is the distributed machine learning. And the federated machine learning is derived from the distributed machine learning, but they are not split the data set to other servers. They actually running the model on the user devices, and also the data is protected on the user devices. So that could protect the privacy and also is a totally different learning scenario compared to distributed machine learning. Because for each client, their data distribution could be different to each other. And when we talk about distributed machine learning, we assume each client have the same distributions. So that's the evolution of the machine learning paradigm, and then it posed a new challenge about the learning objective change. Here we will spend 6 pages to introduce the taxonomy of the federated learning, because the most usual way is have a central server to coordinate all the collaboration between the clients. So we call this is a centralized federated structure. Someone proposed the decentralized federated structure because that one is very hard to converge and also have a lot of issues about communication efficiency and the learning efficiency issues. So it's not the mainstream methodology, and the centralized will be much efficient to implement the federated learning. There is also have a horizontal federated structure. That's they usually have the same feature space, and then each client have different represent different end users, but the feature space of each user are the same. So this is called horizontal features federated structure. That is the most used way in the federated learning. There is also have vertical federated structure. That could be one, for example, take an example in the bank. So you can borrow money from one bank, and also you can save your money to another bank or borrow the money from another bank. So then you have multiple records in different banks. So every time if the one bank want to do a quick approve of your for example for a small size loan, then they probably need to get all your track record to estimate the possibility to give that loan to you. So that means one user will have different records in different banks. So this is called the vertical federated structure. And the similar scenario could be in the hospital. You could reach a different hospital and the clinics to have different records stored in different hospitals. So every time if the doctor want to make a full understanding of your history, they need to collect the data from different hospitals. So if we want to have an intelligent assistant for medical related recommendation or applications, then they also need a way to get your track record or your history record from different organizations. So that is called a vertical federated structure. There could be another way is a transfer federated structure. That is normally transfer the data from one source to another source. So probably you have full access for one organization, and then you want to train the model at here, and then you want to get the information from other sources. So that is called transfer the federated structure. For all this taxonomy of federated settings, they are similar, but could be used in different scenarios. So I won't go detail of that comparison, but feel free to get the survey paper of that. Yeah, so normally when we talk about the federated learning in industry practice, there's five key aspects you need to think about. The first one is the collaboration parties. It could be smart devices, or could be a hospital or bank that will have powerful computation resource. And the second one is about the feature alignment setting. Are they share the same feature space, or they are in different feature space, or are they belong to the same customer or belong to different customers? So it's a feature alignment setting. And the network setting is do you have a coordinated server, or you want to be full decentralized? So this is one thing you need to think about. And also you need to think about the heterogeneity setting. It could be the data distribution could be different or could be the same. And the configuration, the hardware and the software configuration could be different. And also about the functionality and the willingness of the participants. That's all things need to be considered when you implement an industry practice. And the last, but yeah, is also very important is about the security. Because from machine learning perspective, most of the federated learning setting assume the environment is trusted. So that means the server and the client are trust to each other, and trust each other will follow the guideline or follow the protocol to do the things properly. But if you think about that is an untrusted environment, for example, the server is hijacked by a hack, then it could be dangerous because they can steal some information from the client. So if you think about an untrusted environment, then they need a lot of workload to integrate the federated learning with other cybersecurity methodology. So, but in today's, most of the methodology is focused on the cross-device, vertical federated learning setting and have a coordinated server because this is more effective and more efficient. And the heterogeneous setting is normally focused on the low ID data set, and the cybersecurity issue is ignored sometimes. We think it's a trusted environment. Now, given the background of the federated learning, and then we are moving to the federated intelligence. We can start with some more challenging applications because, for example, we can think about the multi-domain VQA, vision question answering, then in different domains that could require a different model to handle that, and each domain require more challenge compared to a slightly distribution difference of the federated settings. So this is a more challenging scenario. And also we can think about other scenarios here about the, we can have a complicated decision makers. Then think about the large language model. They usually have a agent system to help to coordinate the communication between the large language model and the different users. So given that the agent should be able to have make a more complicated decision in a large scale multi-agent systems. Other scenario could be about the complicated task decomposition. For example, a task could you just give a high-level command. So you want to have an agent to help you decompose or understand what your intention and get back get your history record and get all the related information and then explain or translate that command to a more complicated or actionable comments, and then send this to subtask, and each subtask could connect it to different could be an robot or embodied AI agent and other things that could take actions. So this is also a scenario that require the federated intelligence to think about because you need to have a different intelligent agent to collaborative to solve a complicated task. Other possible applications could be collaborative inference. So if one task is coming to a particular devices and because your device maybe have limited, you have a virtual assistant with limited capacity. So sometimes some tasks you are not able to solve by yourself. You can distribute that part of the task into other devices that could solved by other devices or could solved by other AI agents. So they can collaboratively solve a task in a software in different large language model or in different foundation models. And all this model could be customized by different personal data set on a pre-trained large language models. So we are trying to unify all these application scenario as we name that is federated intentions. In the future, we think about the hospital or each individual users or each AI agents, we are connected by the web. So sometimes you are talking, for example, in the web, you're talking to someone. You don't know is a real human or could it be AI agent, or could it be sometimes could it be AI agent with a dog or AI agent with a keys or whatever. So this could be more complicated in the future of the web intelligence. So we need a new we need to define this scenario and also rethink about the challenge we should target in the future. So the possible connection, the entities could be a hospital, bank, could be individual users, could be smartphone, computer, could be a robot, because currently a lot of robots have installed have deployed AI agent as well. And also it could be a self-driving car that can connect it to the web and also collect a lot of sensor informations and also make a lot of decisions. So if all this connected to the web, so what the future should looks like is this way. And if we think about that, we defined all this should based on the user's customized foundation model. So everyone should have a customer or at least one foundation model, or could be a set of different foundation model. And we are thinking about the heterogeneity becomes quite a challenge because there could be various types of heterogeneity, could be from different hospitals or cross hospital to bank or cross hospital to your smartphone or could hospital with your smart devices to monitoring your daily activity. And it also could be a hospital with a robot, could be the robot to do some operating surgery. So that's all this could be connected in the web. So if we want to ensure that model can collaborate to each other, we need to have a fine-grained aggregation. It's kind of a fine-grained collaboration to ensure they can exchange information, and every intelligent agent can evolving or increase their intelligent ability by absorb the knowledge or absorb the experience from others rather than just focus on himself. So this is a way we need to ensure that they can evolving and in a collaborative environment. And we also need to make sure there is efficient communication and learning because due to the limited capacity of the communications and also computation efficiencies, that is quite important. So that is the 4 challenge, I think, in this future federated intelligence scenario. The collaborative mechanism in federated intelligence could be, at first, we need to have a cluster federated fine-tuning because we did have a pre-trained foundation model. It's like a human. Everybody is born with the was born with the basic intelligent ability. Like a baby, they have a basic understanding of something, and of course, they are growing up. When they're growing up, they can get more. They can get more advanced intelligent ability. So, but different in the future, when they're growing up, they can be belongs to different groups. So different groups should be combined together and then learn to each other, and then that will be more efficient way rather than make sure everyone learn the same thing and be the same one. So that is the philosophy of traditional machine learning, but it's not for the federated intelligence. Federated intelligence is trying to make sure that you can start with the same point, but you can end with a different point. So they are encourage the diversity of the learning process and also the learning objective. So that could be collaboration from a group of similar users. Also could be combined in a hierarchical structure. That is the most common way for the collaborations. And we also need to figure out a parameter efficient fine-tuning mechanism to be fit into the federated intelligence, because consider we have a deployed pre-trained foundation model. So how to make sure they can increase or improve their ability is quite important. So at this stage, parameter efficient fine-tuning is the fundamental technology can support the growing up of the federated intelligence. And we also need to think about the convergence behavior, because sometimes when you fine-tune a model, you need to make sure that it can converge to a particular objective rather than learning from for a distracted objective. So you need to preserve the generalization ability, also have a balanced personalization between generalizations. Okay, here is an overall picture of the collaboration mechanism in federated intelligence. So here we want to explain why we uplift the federated learning to federated intelligence, because normally machine learning is is a type of AI methodology, it's a subdomain. But machine learning is trying to infer the hidden probability of the random variable, and by using the limited observed data. Once the model is trained, you can use that model to automatically provide the service or provide the do the inference in an automatic way. That is, we could say this is a very simple automation mechanism. But when we talk about AI, just in a broad sense, it refers to the technology designed to replicate the aspect of human intelligence, so it have more diverse requirement. So the AI have the ability to learn, but the most important thing is they have the ability to make a decision. So they can operate different machine learning models or AI models, and they can they know when and how to use each one and help them to finish the problem. So in that case, they are able to integrate or interact with the environment and make the decision. And so it's more have more high-level intelligent ability compared to the machine learning model. So in summary, the machine learning model or foundation model is the base of that federated intelligence. But now we post a new, more challenging scenario, that is how to solve or how to handle more complicated scenario and make the AI agent in a federated setting become more robust and more with more high-level intelligent ability, and also help make sure they can have the ability to interact with the environment, and also they can improve their ability by collaborating with others, and also absorb the experience and the knowledge from others. So it's a pure objective of the artificial intelligence. Okay, now we move to the part two. That is focus on the framework of federated learning intelligence. Now we've start with the learning perspective, because this is more closely linked to the existing technology. So part of the knowledge, part of the methodology actually is derived from the existing federated learnings, but they still have, yeah, we just selected some of methodology that it could be feasible applied to the federated intelligence. So we will have a few subtopics. We can start with the communication efficient. Yeah. Just recall about the scenario of federated intelligence. We have more challenging scenario for the future of web to connect the different intelligent agent behind of the devices. So as we mentioned, everyone we have a pre-trained foundation model as a starting point. So the following task is they need to learn the knowledge from your personal data or from your interaction history. So we need to think about how to fine-tune or how to update the foundation model to make sure they can quickly fit into your personal requirement or can understand you better. Yeah, here is a few this is a few methodology or strategy to update the model. The first one is trying to update the full model. It's normally it's infeasible because the foundation model have maybe have millions or billions of parameters. If you for your own data, you maybe just have hundreds or thousands of training samples. It's not feasible to update that model in a full size. If you really want to do so, then it will destroy the generalization ability of the foundation model. So the research community proposed the parameter efficient fine tuning. That is there's a lot of way to do that. The straightforward way is try to just update a part of the parameters, not the full parameters. For example, you can update the last layer of the foundation model to make sure that could be connected or aligned to your targeting task. Some strategy is trying to insert the adapter into the pre-trained model. So every time you just need to update the adapter rather than update the pre-trained foundation model. And also prompt and other fine-tuning methodology also invented to update the model to ensure they can get more knowledge about that. So I think most of the methodology actually comes from the large language models, and then you can get more idea from that, and then you can choose which one is actually suitable to fine-tune the model in the federated intelligence scenarios. Here is a quite simple explanation of the parameter efficient fine-tuning. I will quickly go through that because this is not a new technology. I would say this is proposed several years ago, but I think it's still okay or still practical to use that methodology to the federated intelligence scenario. That could be the fundamental component to construct the federated intelligence system. Yeah, prompt learning is quite also straightforward because as we mentioned, the left picture is say, okay, it's infeasible. We update the model every time for different task batch. So we need to find a more efficient way trying to put the task descriptor and the other prompt related or the description knowledge together and then put everything into the pre-trained model. And this model should understand that and automatically make the decision in an accurate manner. So by this way, you just need to think about turning the prompt rather than trying to get a new foundation model. So this is a way to it's a very efficient way and easy to use way. Other way is could be use the adapter to turn the foundation models. This is also you can put the adapter plus with the foundation models together. Then every time you just need to change the adapter, you don't need to change the parameters of the foundation model. This is also another efficient way. You can easily get a lot of papers by search it. And I would talk about this low rank adaptation. That is a recently very hot topic, and it's also have been proven very effective. And if you look at the left picture, you can have pre-trained weights, pre-trained parameters. So every time you get an input X, then we go through two channels. One is pre-trained parameters, and the right channel is another parameters that you can go through, and after that you will combine them all together to be the final output. So the left part will be fixed, is pre-trained, and the right part, the orange part, could be changed and updated and learned or fine-tuned. The interest thing here is quite communication efficiency, because they will decompose that the right parameter matrix to two vectors through the matrix decomposition. So every time you just need to produce two vectors, that can save a lot of communication cost. And also as demonstrated by the success of lots of LoRa related methodology, that one is quite effective to produce the personalized information. There is if you search the related topic of the LoRa with federated learning, there's a lot of paper available, and I think most of them focus on how to use the LoRa to preserve the personalized information of different clients. There could be, for example, the most straightforward way is everybody have their own LoRa and then aggregate its server, but still have a personalized LoRa at each client. So each client have a personalized LoRa, and they also have a shared information at server. And about they have a few advanced methodologies that talk about how can we just mask a part of that. For example, mask A, and then make sure we only change the B, and because every time if you want to upload all the two vector to the server, the aggregation still have problems. So they need to get a way to solve that problems. Here is a federated LoRa that is similar to the others one, and they just focus on have a think about the differential privacy that with privacy protection issues. And here is another way of the federated LoRa, and they have two LoRa at each client. So one LoRa still share the information between the users, and another is a personalized LoRa that can preserve the personalized information. Then eventually they will have a weighted mechanism to put that two LoRa together. So if you see the left picture is the if other federated LoRa works, that pre-trained model plus LoRa, but you see the middle one, you will have a globally shared LoRa and also have a personalized LoRa, and all this combined together and add to the pre-trained model. This structure will give more flexibility to implement the knowledge sharing across LoRa, rather than a simple structure that combines everything in one globed one. So it provides more flexibility, or have more powerful capacity to preserve the personalization and the general information. Now we move to the second subtopic of that framework. The previous one we talked about the basic mechanism to fine tune the foundation model that could be the that is the basic of the federated intelligence. The second one is about how they exchange information, how they collaborate together and aggregate the model parameters. It's worth to noting in the federated learning, they normally exchange information by aggregate the model parameters. The different thing is we need to worry about is what type of information or what the information is preserved in the parameters. Here is the heterogeneity issues of federated intelligence. That one is more complicated than the ordinary federated learning because previously we just think about a simple low ID or that is slightly different to each other. But now the heterogeneity become more complicated. For example, the statistical heterogeneity it normally refers to the distribution different to each other. But in a federated intelligence, the heterogeneity could exist in the same time. That could be have a label low ID. So that means the distribution of the label space are different to each other, and also have a heterogeneity on the input space. So if you need to handle these two heterogeneity together, then that could be a challenging scenario of the current federated learning, and also need a more advanced methodology to tackle these practical scenarios with different heterogeneity situations. For the system heterogeneity, yeah, that is also quite practical issues. You need to think about the computational capacity, the network communications, and the energy constraint is also quite important because most of the participants actually is the smart devices. They can't afford a lot of energy consumption for training a model or frequently update the model. So for this case, yeah, we also need to think about in the future of the web. So all these different devices are connected in the web. So how the intelligent agent could understand their system configuration and then perform their model training or model updating in a smart way. So this is also a challenge we need to handle in the federated intelligence in the web. Here is the explanation of the statistical heterogeneity. It's still for example, we have clients, 3 clients, and each one each shape belongs to each shape represents different different labels, could be different label or could be different type of task. And then all these clients have different data, and part of them can share to each other. For example, client 1 and client 3 can share some information about the triangle, and the client 2 and the client 3 could share some information about the circle and the rectangle. So they could partially share the information, but eventually if in the web scale, you could you cannot unify all these feature space in the same. So the scenario is you just need to find someone, a group of people or group of end users that is similar to you, but they might not be the same with you. So that is the diversity or the personality exists in the real world. So we need to make sure that the federated intelligence can understand and can tackle this type of statistical heterogeneity in the real applications. It also requires us to have a better modeling capacity to use this kind of data. From the previous experience of federated learning, they normally do the personalized federated learning. That is quite a popular methodology in federated learning. But For example, they can treat giving a shared models. They just use the last layer to preserve the personalized information or personalized the parameters. So they can use the first, for example, 100 layers to preserve the shared information, and use the last layer to preserve the personalized information. So this is a straightforward solution to tackling the heterogeneity in the federated learning. But that is quite it works okay for the labor low ID situation, but if you want to hold two scenarios, or you want to handle the input, the heterogeneity in the input space, then that could be not enough to handle that. So, but this still give us some idea that the partial model updating is a quite effective methodology to preserve the personalized information. So even in the first personalized intelligence, federated intelligence, that is still effective to handle a special kind of heterogeneity. We also think about cluster-based model aggregation, because as we mentioned, it's very hard to ensure everyone in the same space. Then what you should do is trying to figure out a group of similar users and then put them together, and then they can collaborate to learn some shared model to each other. So this could be a more effective way to handle a large scale end users with different background and different preference. Actually, similar strategy have been applied in the marketing, in the business marketing. For example, the customer segmentation of doing marketing. Every time if you want to make a marketing plan, if you want to make a marketing campaigns, then you need to segment the customer to different group, and then different group you have a targeting the policy to attract them or to service them. So this is similar to our cluster-based model aggregation. We're trying to use different group to aggregate the user information or get the user preference by cluster or by groups, by interest groups. So for the cluster-based model aggregations, you can do both the no IID and the IID environment. That's for the no IID, you can have different cluster to handle that, and in each group that is in a, we assume that is in a IID environment. This is the simplest case as show the picture. But in the reality, we think that could be a soft classroom, may be a better to capture the groups, because here we use the hard cluster to separate the user to two distinct groups, but sometimes the user could be shared by two groups or by three groups. So if we think about that way, and then the cluster and the groups could be overlapped with each other. So that could be a new research direction to think about that, to class-based model aggregation and based on the overlap of clients. So here's the technology of the class-based model aggregations. Each time you need to learn the models, learn a shared model for each class, and then this class also shares the information at the server in a central server, and to make sure they can do the clustering and the model aggregation in iterative steps. As we mentioned, if you just use the one level to capture the heterogeneity, yeah, it works for a simple environment. But if you want to handle a more challenging scenario, the hierarchical grouping might be a better choice or can provide a more powerful modeling ability to capture different types of shared interest or have shared preference. There's a lot of hierarchical structure in our real world. This is a most common structure in a company. For example, you can have a hierarchical and a different group of people working on different tasks with different objective. And finally, they will collaborate in a higher level to solve the complicated problems together. So we can borrow this idea from that collaboration structure. It's a bottom level. Each group can have a more dedicated task, and then when you move to the higher level of the hierarchical, they can be much more different, but they can collaborate to solve more complicated problems because they collaborate. I think they because they are different, so they can collaborate to each other. So that's the high level concept. But in the bottom level, it's more like they are similar and they can jointly solve just a simple problem better. So they have different assumptions in different levels. So this is the hierarchical model aggregations. Here is a recent work about trying to capture that. I would say this is the extreme heterogeneity issues that use multiple levels to capture the personalization informations in different levels. And here, each model or each personalized model or each client actually have a bunch of models. That model is from different level. What we need to do is just add all this model into one would say one bond or could be integrated into one network, similar to the ResNet. Then all this model can combine together to an entire model to provide a personalized service. But the benefit is different level can capture different levels of shared information. So it can provide a fine-grained personalizations of different users. So this is this is a hierarchical structure to capture the fine-grained heterogeneity issues. There's other way to solve that extreme heterogeneity issues. That, for example, you can use a graph to capture the heterogeneity, because sometimes, for example, in the scale of millions of users, you don't want each user to be the same with others. Otherwise, if you put millions of users preference together, then you will get nearly a zero or a Gaussian noising data that's with no personal interest in that. So every time you want to share the information just in a small group. For example, you can share the information just with your friends, maybe 10 or 20 friends in the social networks. Or sometimes think about the traffic network. When you predict the traffic flow in one point, you just need the information from the related or joint point from in a traffic network. So a lot of similar things that could use that graph-based aggregations. So that's giving you another way to handle more challenging heterogeneity issues. Here is another way to think about the heterogeneity, because sometimes we think the input space could be heterogeneity to others. So we can use two embedding network to handle the shared information and the personalized information separately. For example, as shown in this picture, the blue part is a shared embedding network that could be aggregate at the server. So that preserve the general information across many clients. The red part will be a personalized embedding network that could understand the general information and also understand the personal information that could produce the embedding as well. So after that, all this general embedding and the personalized embedding we are joined together to be decoded to get a representation reconstruction. This is one way to tackling the heterogeneity issues. Similar way could be think about the representation alignment, because for even given the same instance in the same feature space, they still have different preference to different label space. So for different clients, they have different preference, and then also need to better align the representation space by to the label space. So this is another way to talk the this is all the way we think is could be useful to tackling the static heterogeneity. The system heterogeneity could be a little bit challenging, I would say, because they actually it's not about it's not about the distribution, it's about the computational capability and the network configuration and energy constraint. Most of the work actually is I would say this is more like an engineering challenge than you need to solve that in that engineering solution space. But so for this case, I think normally you can still use the similar strategy. For example, you can cluster the similar devices or they have similar configuration and put them together in the same group and then make sure they work together. So this is one straightforward way to solve that system heterogeneity issues. And moreover, sometimes because the computation capacity is different, so sometimes the different clients have different model architecture. For example, your smartphone have a model with 1 million parameters, and another one have a high performance computer. They can have a model with 1 billion parameters. So when you collaborate to each other, so that will be a challenge how to ensure they can share the information or they can collaborate to each other. One protocol is like you can do the knowledge distillation between them, because because you cannot put the model parameters together by aggregations. So the only way you can do is the distillation the knowledge, because knowledge distillation is based on the output. Knowledge distillation is the common technology. You're giving the input into two different AI models. For example, you put the input to a big model and get the output, and then you get that input-output pair back to the small model. You can make then using that way, you can train the small model in a better way. So knowledge distillation could be an effective solution, and there's actually have a few research papers talking about how to use knowledge distillation to solve the model heterogeneity issues. Another way is trying to share the information from the representation space, rather than share the model parameters, because the embedding or the representation is the output of different model. So what you should do is try to align the representations rather than align the model parameters. And when you align the representation into the same space, then this could give the feedback to different model architectures to ensure they can learn, they can produce the representation to the in the same way. So this is a quite soft way to force the different model to learn to the same objective. Here is the prototype-based aggregation. This is one special one. The prototype normally is averaged mean of the label representation. So you can also do other representations-based aggregations, but sometimes you need to be aware of the privacy-preserving issues, because if you share the too much representation information, that could leak could cause some privacy issues. Yeah, the last subtopic is about learning from change, because we are talking about the intelligence should be able to evolving rather than pre-trained the never changed. Basically, we just the first one is the test time adaptation. The test time is when you train a model or train a foundation model in training and the validation stage, but when you apply that to the real applications, that means the test time. The test data could be different with the training data. So that is trying to mimic the real situations. Every time when the model sees some new task or new data you never seen before, how your model can handle these situations. So that is trying to ensure the model have the ability to handle the unseen data or unseen tasks. The straightforward solution is trying to figure out the relationship between the training task or training data between the test data. So you need to build a relation graph, or you need to find a mechanism to measure the no matter it's a similarity or relationship between the training data or training task and the task data. So by doing so, you can ensure your model can handle the task data quite easily. And here, normally the training data could be, or maybe there's a strong assumption is the test data could be comes from different data sets in the training data. So so every time you do the test, you need to figure out the relationship with multiple training data sets and make sure they can solve that problem. Because your task may be not the same with the training task, but the key information could be comes from different data sets from your training data. So that is called the test time challenge of the federated intelligence, also have a need to be solved. Another scenario is about the continuous learning. The continuous learning is normally think about giving the same client the preference, or the preference could be changed as time going. So for example, today I want to reading the book or watching movie for romantic movie. For the next day, for Sunday, maybe I want to watch a movie for the for another cartoon movie or for other type of movie. So the user's preference actually changes all the time, and sometimes the user may be impacted by the friends, by other unknown sources that they change their mind. So given that scenario, we need to ensure that the on-device virtual assistants or the on-device agents can understand that change or detect this change, and then update their model promptly to make a quick response to that situations. So from machine learning perspective, then the learning task is not going finished after training. So the training, when you finish the training, is just the start. When you apply this to the real environment, they still have a lot of learning processes is ongoing. That is continual learning. So for this type of task, if we are thinking about every agent can have a continuous learning ability to understand the users' preference change, then that could be a very useful capability to implement the federated intelligence. They already have a lot of continuous learning methodology that apply to the federated settings. The client shift is another challenge scenario because in most of the time a web service or a learning system is trained to serve a particular group of client, but when you get as your business grown, you will have more and more different users coming, and then they have more diverse backgrounds. Then the client shift, that means the client's preference will be changed. And for the new, especially for the new client, they will come with the new preference, and that will cause a challenge to the federated intelligence system. You need to ensure they can understand the distribution of the preference of the new clients, and also understand all these client shift related is from the input space and the output space. They could be quite different. So this is also a challenge to ensure the federated intelligence could be working in a right way to keep going up. Okay, this is all my talk for this session, and I think we can have a coffee break and then come back for the following two parts. Thank you for listening, and happy to talk to you at the coffee break. Thank you.
Good job. Very busy. Yeah, we were planning for the conference, so it's a story on.
Yeah, so I'm going to my one to the first one, then I can
Yes.
fully release it to the other to the past.
You still have another session. also would be. Okay. I read it now. Is there a description also? I tried to see the description. Description is not there, right? Oh, yeah. It's okay. It's, but we will use it for just the title. Yeah. The description is not included, right? So, okay, yeah, I tried to find it. You just have to give it to us. Yeah. You will do it. Yeah, okay. But anyway, we will have a meeting. Tomorrow, lunch. Tomorrow lunch. So we need to do. So this tells you how much how many people, how much is. And then plus the comp. The comp is under something. Usually 200. Yeah, usually 200. So you know how to choose. It's 60 volunteers. And most of the time, we've done professional recording. You would get something you think, yeah, okay, go, I'm gonna stay here and do the work. I even do the rest of the water, but I use it.
我有点小，好像。些东西，放些其实是20嗯，你看时间嘛，可能拍到就差不多跳一跳。
Good morning, everyone. First, thanks Guodong for his introduction to federated intelligence. And next, in part 3, we will talk about federated intelligence from an agent perspective. First, we will explore two frontier research topics: the application of federated intelligence to large language model agents, such as the ChatGPT and Claude. And then we will also explore its application in the embodied AI agents, which majorly compromise own device intelligence and the robots. And finally, we will extend the discussion to concrete challenge and research of enable federated intelligence among heterogeneous agents and devices. So first, we will have a new definition to the federated intelligence from an agent perspective. So let's begin with the first this perspective. So for example, in a decentralized federated intelligence system, we can naturally view the overall architecture of a federated agents or federation, each representing an autonomous intelligent entity, usually implemented by a large language model or foundation model. Then each agent is ideally equipped with a foundation model that provides broad capabilities. Usually it can handle reasoning, communicate, and adapt to diverse tasks. So for example here, one agent operating in a clinical environment might specialize in diagnosing diseases based on patients' records or test results. And another agent in the hospital, it might be embedded with a hospital system, usually focused on treatment planning and coordinating therapies or medication schedules. So, if we adapt one in the pharmaceutical companies, it might be tuned to develop drugs or prediction molecular efficiency or other clinical trials. So, the question is, how could these agents to collaborate? So, okay, so each as here, each agent usually contributes to its domain-specific tasks. So, for example, clinics, we have diagnosis agents, and in hospital, there are treatment agents. So while retaining the ability to collaborate across, from the model perspective, as Guodong has introduced, we can co-training or co-tuning the model, but our goal is to make them collaboration. So for example, we can have the hospital agents to call some diagnose agents to have to track some patients' records or development of some diseases. So in the federated intelligence, we decompose this collaboration into two parts. One is the cooperation, and another one is the collaboration. In the cooperation, we usually assume that these agents cooperate by independently training their own local data and contributing model updates toward a shadow object. This pattern is kind of like the conventional federated learning. So the goal is to really optimize a compatible global model. And additional restrictions must be preserving the privacy or autonomy of their local data. So another one is the collaboration. Clients or agents should communicate to refine global policy or share structured knowledge. This kind of the call and response schema in the large language agents in modern AI systems. Here, agents do not merely submit isolated updates. Instead, they extend structured knowledge, refine shared policies, and support each other's learning. For example, here, hospital may cooperate by training a shared treatment model, improve overall performance, and at the same time, they may collaborate with local clinics to track patient progress, and with pharmaceutical companies to evaluate drug efficiency. So this form a dynamic and adaptive network to mutually reinforcing expertise. So the challenge here is different from the conventional federated learning. They have more complicated tasks need to collaborate. Say we have the cross domain or actually they have very different tasks. Another one is comparing to the call and the response schema like the ChatGPT, which there is a coordinator agent like the ChatGPT itself to call other sub agents. So we might ask ChatGPT to help evaluate disease, and it will call subtask specific agents for diagnosis or treatments. But here we aim to allow these agents to collaborate directly without a central coordinator. There have been some works extended to this research field. Here we focus on two frontier tasks. First is the large language model agents. So here is a standard of the most popular large language model agent system. First, we send some promos. We send some promos or some words to the agent, usually called the coordinator agent, and the agent will decompose it. This progress is usually called the chain of thought, and it will generate a sequence each for one task and include some subtasks and the agent it will call, and then the coordinator, usually the ChatGPT, will organize the task and make a plan. The first it will call which agent to complete the task, and then the next, and evaluate the plan and generate the final promos, usually some commands or some promos which will be sent to this subtask agents. And then each task agent will influence or run the code locally and independently. And then they will send back their running results back to the ChatGPT, and ChatGPT will collect these results and synthesize them into one sentence to feed back to the user. So let's look at this progress. We can find the red one here, usually implemented by a central agent, and it's rely heavily on the coordinator agent, which is usually opaque and controlled by some big company. And then here are the subtasks. These tasks only be called by the central agent. They work independently and usually lack cooperation. Say the example of the hospital and the clinic. So suppose the first one is a clinic agent, it will not cooperate with the hospital agent in this case. So, recent work have some improvements and bring the concept of federated intelligence to this scenario. The first work here, the red one here, proposed a decentralized framework for fine-tuning large language model agents across multiple nodes. So like this paper proposed the decentralized method which allow these clinic agents to collaboratively train coordinator agents. It allows us to get rid of the centralized large language model. So they may call train and deploy the agent on their own. So for the new promote or request, it does not need to send it to a central agent. So and another work here is the blue one. This work introduced a communication protocol, kind of like the most recent the MCP, the model contact protocol. It allows this green one, this subtask agents to collaborate. So it's kind of the multi-agent system. So for example here, the clinic and the hospital and the treatment agent, they can kind of collaboration to solving the problem. So these agents are now no longer independent, and we can share some structured knowledge and in the federated intelligence way. And this allows us to imagine the future of the AI agent system. So from the original, the rule-based agents, and then we built the model and using the reinforcement learning algorithm to tune the policy model or the reward model to build better agents, better and adaptive agents. Then now we use the large language model to help reasoning, planning, and generation action sequence. And then now the federated agents or the agents in the federated intelligence system, they further allow each agent to collaborate directly and cooperate for the same task by sharing knowledge or to handle complex tasks. And another important thing is as each agent works on its own data, and what they are sharing is the aggregated or the structured or the extracted knowledge. It can help us keep our privacy locally and can help us decentralize. We do not rely on specific commercial products or send our data to those companies. And another interesting application is the embodied AI agents. So we may first to introduce what is embodied AI. Embodied AI could be some robots, or it could be a automobile or robots or robot arm or something. And recent works have deployed large language model based models to allow this devices to exploit the world by itself and to handle complex environment. So the difference is here is not to generate response, it's to exploit the physics world. It's usually powered by a tailored foundation model But one thing worth noting is as this devices usually have a limited computation capacity, so it does not work on something like the GPU cluster. So usually the model deployed here is lightweight and carefully tailored. So the first work is from Google. It proposed the robot transformer one or the RT1. Here, the Google leverage two different robots. One is the robot arm to collect things, and another one is to put things on the table, and they collect data from these independent robots or the agents and aggregate those data to train transformer structure agents. And they also release the benchmark dataset in the following work. So it's called the X embodiment. So it have about 22 different types of the robots and with over 500 different tasks. So then with this baseline, there have been plenty of works in the last year, and most are based on the vision language action model. It's actually the vision, the foundation model that tailored to generate action sequence. So for example, the OpenVRA is based on the Llama 2 and combined with some vision transformer to exploit the surrounding environments, and also with that clip to combine the human instructions. So as these agents worked independently on each robot, so more recent work have explored the federated intelligence collaboration among these agents. This work tried to train a coordinate agent to coordinate some robots in the environment. So for example, some I work in the bedroom and others on the living room. So they hope to coordinate these robots to complete different tasks simultaneously. And another work is a kind of federated learning work. They try to train or improve a centralized agent model by a set of different robots or different agents on different tasks. Then beyond this work, beyond the embodied agents and the large language model agents, so we can collaborate among agents from very different tasks. Say we can have software development agents which help us coding, and we can ask it to cooperate with some, say, the industry engineering agents. So it will generate some software or programs to handle complex industry engineering work or manipulate some robots. So this broadly extend the centralized and the conventional federated learning and the centralized large language model agent system. So it help us to achieve some kind of collective intelligence, which formed by dynamically and adaptively collaboration among different agents from different tasks, and they usually have different structure or architecture and knowledge. So this raises two key challenges. Is different from the call and the response schema in the current large language model system. So these models are basically heterogeneous, and they are designed to handle heterogeneous tasks and work on heterogeneous environments. So how could we, the first question is, how could they change their information? Either they are cooperate for science or knowledge or collaboration to help each other reinforce their performance. So here are some inspiring works here. The first is we can left each model to handle it, or each agent handle its partial or layers or adapters on its own task and the rest for the global task. This is a very straightforward but effective strategy. So in this approach, an agent might co-train a shared subset of model components, and this could be a shared classifier or shared backbone. This is quite common in the conventional transfer learning and model adaptation tasks. And in the recent transformer structures, the most effective way might be build an adapter modules here. So those agents share their common knowledge by the global shared parameters. This could be heavy and complex. And then for their own tasks, they might fine-tuning or learning a lightweight adapter here. And this work have shown that this partial adaptation strategy is sufficient to match the performance of fully adapted models, which means either we adapt the entire model on a task, or just this lightweight adapters, they will have very similar performance. So we don't need to have very heavy computer load. So these are basically based on the parameter sharing. And another popular and emerging way is to share schools according representations. A first and classical one is the prototypes. A prototype could be a shared abstract representation for specific labels or tasks or concepts. So each agent to map a representation of their local data into the prototype and the shared representation across clients, and different clients or the agents may align this representation by the label or the concepts. And a similar one is the shared embeddings. So in this work, each agent is a recommender model. So they encode an item into a local embedding and share it into to the server. And the server can learn the relationship of this agent. So it can synchronize the update and the personalization of each local recommender model. Difference here between the item embedding and the prototypes is the prototypes are usually representations with explicit semantic meaning. So we can say similar prototypes or prototypes have similar representations, usually have a similar semantic meaning. In contrast, the item embeddings usually from a latent basis. It's a compressed abstract representation space capturing fine-grained information without explicit semantic labeling. So it's kind of like the acts of the semantic space, and we can represent the client by combination of these item embeddings. And another one, the most recent one is sharing the promos. So it's usually cooperate with the promote tuning. So when we do not share the model, but we ask the model to output promotes, these promotes will capture the shared knowledge among different agents, and so we just need to share the promotes, and then each agent can take the promotes as information from other clients or the agents. And a very fancy advantage of promotes is this promotes usually acts as a language level interface. So it allows us to read or understand what is shared in the form of natural language, not just a representation or an embedding. So it have better interpretability. So here is the recent research on how to collectively across heterogeneous how these heterogeneous agents collaborate, rather without knowing their parameters or architectures. Another problem when we bring federated intelligence into agents is the conflicts and the concept alignment problem. Here is a very typical example. So here's a man asked the agents to place the plate on the tray. So the robot one is an agent trained in the environment of restaurant. So he thought the tray is usually a flat surface, and the goal is to balance the plate upright and put it in the center of the tray, prepare for carry. And another agent is the trained in the kitchen. So in his mind, the tray usually refers to the drying rack, and the goal is to insert the plate vertically into the slot, so it can air drying very fast. Here two agents have very different chain of thought, and it will lead to very different results and actions. And now we need to coordinate or align the concepts and avoid this kind of conflicts in the federated intelligence system. So we can find this conflict usually results from the environment the agents is trained as. Agents in the federated intelligence system usually trained on its local data and collaborate through either parameter sharing or representation sharing. We have no idea about its training environment, and this environment usually leads to difference in data preference or other divergences. So, and the federated intelligence is a decentralized system, so there are usually lack of alignment mechanism to align with concepts. So one solution is to disentangle the latent representation applied in this system. So for example, here the numbers are entangled with different marks here, and we may use two encoders. One is to learn the shared the numbers, which is applicable on all agents. And another one is to minus these numbers from the original input and to get the context or the environment information here. And once disentangled, we can combine them as the promoter tuning to the agent model, so they can cooperate without conflicts. Another way is the hidden space alignment. For example, in our previous case, so the problem results from the ambiguous about the word tree. And here we can decompose the Latin representation of the agent model. So along this axis, it represents the tree, and another vertical axis represents the environment. So we can find the so we can decompose the promotes into more specific commands. Either it should be implementing the tree in the kitchen or in the restaurant. And let's quick glance at the federated intelligence from the agent view. So the next Shengchao will help us discuss more complex case applications and the open challenge in the real world. Thank you.
Okay, thanks, Paul, for the detailed introduction to the future direction of federated intelligence in agent perspective. So next, I will exploring real-world application and open challenges in the exciting field. And as we know, federated intelligence is an emergency and innovative concept that take traditional federated learning and federated foundation model to a new level. So in the upcoming session, we will to discuss the related application and the challenges, and along with some potential solution. So in summary, we have divided the real-world applications and the open challenges of federated intelligence into 6 key points. For application, we have retrieval augmented generation and recommender system, and some with the time series foundation model and the healthcare foundation model. And for learning scenarios, we will discuss the language model systems for cross-silo and cross-task learning, and generative learning in federated intelligence. And for challenges, we have 6 points, including on-device agent deployment and agents personalization and communication efficiency, allowing multimodal data for collaborative training, policy and security, and explainability with multi-agent collaboration. So first, we give overview about the 4 main application and the learning areas in federated intelligence, and we divided these 6 points into 4 domains. The first one is knowledge and the information system. It focuses on how knowledge and the information system can be enhanced by federated intelligence, and especially in large language model modeling and the retrieval augmented generation. And for personalized and predict system, it focused on building personalized and predictive systems through federated intelligence, like recommendation and time series. For creative and generative system, it is specializing in generative learning applications that can generate images, text, and or multimodal content with federated intelligence supports. And for healthcare and the sensitive domain, it focused on used the federated intelligence in some sensitive domain or process some sensitive data like medical data. So in the first subsection, I will introduce the federated intelligence on real applications like retrieval augmented generation, healthcare recommendation, and time series. So this page shows the retrieval augmented generation in federated intelligence. Just like federated retrieval augmented generation is technique within the federated framework that use distributed retrieval to integrate heterogeneous data from multiple organizations or multiple institutions for collaboratively generating high quality outputs. And this slide gives a simple workflow of retrieval augmented generation in federated intelligence. So first, the process begins with user requests. For example, the user maybe give a ask. Next, the query is sent to the request mediator. We often use the large language model based agent to add the request mediator. So which server as the central controller, it's decided what to do with the query, and it will be as the judger to do some judgment about the query. If the searching is required, it identifies which data sources are relevant and avoids unnecessary ones. In this example, S2 and S4 are selected, while S1 and S3 are excluded. And then, if no retrieval is needed, the mediator can directly generate a response. So then the chosen data source performs distributed retrieval and returning relevant information to the mediator. So the key advantage of this workflow is its efficiency and the accuracy, and it don't like traditional centralized retrieval, and it can use the different data source or different knowledge base database to enhance the final outputs, and this final output will be a cohesive response back to the user. This page shows the healthcare in federated learning, and it focusing on the areas that dealing with some sensitive data like medical data or some medical imaging or medical reports. It enhanced privacy protection and multimodal data integration through federated intelligence. Like we accept the federated intelligence system can perform different downstream tasks like medical image VQA and medical signal VQA and some medical image classification. But to achieve this different task require collaboration between different model. That means if we have different agent or different foundation model in the system, we need to effective way to achieve the multi-agent collaboration in the healthcare task. This page shows the details of healthcare in federated intelligence. So what can federated intelligence do in healthcare? Just like unlike traditional model to use the federated learning for a single data modality. Federated learning enables the development of a unified framework that capable of processing multiple types of healthcare data, such that medical imaging and medical report and the medical outputs. So the unified framework can be applied to different downstream tasks like report generation, image classification, and the image generation. So this show a framework that to address the unique challenge of integrating multiple medical knowledge into a foundation model or federated intelligence system, and while adhering to strict privacy protection. So this framework use the cross-silo federated structure and avoid the need for centralized data collection, and it widely used in healthcare domain. So next is this slide shows the federated intelligence in recommendation or recommender system. It is a framework that enhances recommendation quality while preserving user privacy and using personalization adapter to improve the foundation model in different user modeling. So in traditional recommender system, user data is centralized for training, and it have significant privacy concerns. But this work built on federated intelligence and allowed client to train recommendation models locally using personal data and sharing only aggregated information with the server. So on the client side, each client use a personalized adapter to learn user-specific performance and user-specific knowledge from local data. And it have adaptive gate learning mechanism ensure a balance between local and global knowledge and combine personalized insight with shared global parameters. And on the server side, ensure the parameters from all clients are aggregated to create a global model that accepted to captures common trends across user. So finally, this framework frees the foundation model layers and updating only personalization related parameters like the personalized adapter and enables collaborative learning without exploring raw user data and ensuring privacy and improve the user specific modeling. This page shows the second recommender system in federated intelligence, and in the architecture, user data remains on client device like the first recommendation system, and the slow federated intelligence system, global and public modules aggregate shared insight from multiple clients without exploring individual and sensitive information from different end user. So this system used some some mechanism like attention modules and global gating network and the transformer layer to model user knowledge effectively, and while parameter exchange as the server ensured continuous improvements. Next, this slide shows the federated intelligence in the foundation model or weather foundation model, and highlight real-world application. So our key question is why process weather data on devices instead of centrally? Actually, global countless weather sensors generate massive and a large amounts of different time series data. So centralizing this data for training large scale and large scale model introduces significantly communication overhead and storage challenges. So federated intelligence addresses this by enabling lightweight but powerful on-device modeling without training large model from scratch using large-scale pre-training data sets. So for the workflow of this architecture, each client adds weather sensors, train a personalized adapter using its local weather data, and this adapter connected a pre-trained large language model, which provided general knowledge for understanding the time series data. Time series data have some similar feature as the text data is they are all there are the sequence data. So instead of retraining the full large language model, clients updated only low rank metrics and can reducing the computational resource and communication cost by communicating only the low rank metrics with this central server instead of 4 model parameters. So this system can predict multivariate weather time series while adapting to local condition using some task-specific adapter, and is an efficiency solution for large-scale weather prediction or large-scale weather data understanding. And we do not use the large scale time series model, and tend to use the lightweight training strategy based on the large language model to reduce the requirement of large scale time series data set for pre-training. And this slide shows the cross-domain time series forecasting in federated intelligence system. The first challenge for the background is time series data coming from various fields like economics, weather, and healthcare and traffic. So these data sets are often solid and sensitive, and making centralized model training difficult or even impossible due to some frequent communication of the time series data. So this slide provided a solution based on federated intelligence and enable collaborative model training across domain without sharing raw data and without training from scratch using domain-specific knowledge or different cross-domain time series. So this framework based on cross-model alignment. Each class aligns its data using some techniques like patching or normalization, and ensuring the cross-domain knowledge alignments across different data formats and these time series from different domains. And then it used pre-trained large language model, server as the foundation, server is the foundation of this framework, and offering general knowledge and adaptability. And from the perspective of the federated structure, and the clients send updates to central server, and where they are aggregated into a global model, and the global model can be adapted in different clients and different domain time series forecasting task. And this page show time series foundation model training strategy based on federated intelligence. So the question is, if we don't use the pre-trained foundation model or pre-trained large language model as the foundation for subsequent pre-training or subsequent fine-tuning based on some parameter efficiency fine-tuning techniques. How can federated intelligence help us to develop a more powerful foundation model that goes beyond centralized training? So this slide introduces federated time series foundation model framework designed to build time series foundation model by addressing the challenge of domain heterogeneity among the different time series. The first challenge comes from the nature of time series data, which span the diverse domain and like traffic, weather, financial, and healthy, and these data sets differ in frequency and often highly heterogeneous case by their have different potential physical constraints. So centralized training is hard to handle this diversity, and due to it simply fills this data in in a large scale data set and feed the data set into the model for training. So it often aggregates out or overlooks some domain-specific knowledge or domain-specific details in different time series. So the solution is based on federated learning to develop a federated pre-training strategy. Is a approach that mitigates domain heterogeneity and it will different time series or cross-domain time series as independent clients and to use some technique like a mixture of experts. It's a specification updating techniques to update its local transformer block and this architecture dynamically active different experts based on underlying representations of the data and allowing for specific processing and additionally, raw aggregation clients can be encouraged to share common temporal pattern instead of some biased pattern. So enabling the creation of a unified time series foundation model, and the time series foundation model can be divided into can be used to different downstream tasks like forecasting, imputation, and classification, anomaly detection. Next, in the subsection, I will introduce the federated intelligence in various learning scenarios like cross-domain and cross-task modeling based on large language model system and generative learning based on generative learning based on foundation model. This page shows federated intelligence in cross-task modeling and which focuses on fine-tuning large language model across multiple clients with different tasks. So in this scenario, each client, such as an organization or device, has unique task and data like answering question and classification or determining logical entitlements. So from the perspective of this federated structure, each client uses a four-region large language model as the backbone, and the client train a lightweight local adapter instead of performing 4-parameter fine-tuning on the specific task and specific data to achieve the personalization of the pre-trained large language model. And this local updated are sent to central server and where they are aggregated in a global model or global adapter instead of a global large language model. And the remaining parameters of the large language model is maintained in each client locally. So in this framework, clients benefit from shared global improvements while retaining task-specific optimizations and ensure data provides. And this slide shows the application of federated intelligence in cross-silo modeling in based on federated large language model system. Which enables the training or fine-tuning of AI models across multiple organizations with different target and different data formats. So imagine a cross-silo environment including different organizations such as a hospital, school, and bank. And each of these organization processes its own types of data, like medical data for hospitals and some educational data for school and financial data for banks. And by collaborating, these organizations can learn more representative and insightful information from their combined but diverse data set. And for example, a school model can benefit from the knowledge of hospitals and banks and gaining insight that improve its educational contents. And similarly, a hospital model can incorporate knowledge from schools and banks for better medical prediction or medical related tasks. So how do this collaboration work? And from the perspective of this framework, and each organization train its local model, and hospital train models for medical tasks, and school focused on subject tasks like mathematics and geography. And the banks works on financial tasks like stock prediction and customer behavior prediction. So this local model are connected by a common backbone deployed in each client, and which acted as the shared structure for collaboration. In this setting, no raw data is exchanged between organization instead of organization and this client, and the central server perform frequent updates about including each client send task-related embedding to the server instead of 4 models. And the aggregated future back to each client to combine its common backbone for enhancing the local model by the unified and common general knowledge from different domain and different tasks. And this framework enables institutions to collaborate effectively and benefiting from one another's data indirectly and without compromising privacy and or security. And this page shows the creative and generative system in federated intelligence, and it's the key question in the scenario is how to use the federated intelligence for cross-domain generation, like medical image and some natural image or some remote sensing image. This slide show the generative learning in federated intelligence, and it combines federated structure with generative model to enable collaboratively training. And in traditional generative model training, data is centralized on a server, and which pose significantly some risk about privacy and some storage. So this framework allows multiple clients which holds different image data set from different domain to collaboratively train a global model without sharing the raw data, and to sharing the raw data or communicate the raw data in central server. So instead, client exchange text embedding instead of for model like stable diffusion and another pre-trained model to achieve communication between clients and the server. So finally, this framework can this framework can achieve cross-domain image generation capabilities, and based on different knowledge from different image domain. For the last subsection is open challenges and potential solution in federated intelligence. And now we have we summarize 6 primary challenges and divided them into 3 topics in federated learning. The first topic is federated intelligence system optimization, and it including on-device deployment and communication efficiency, and focused on how to adaptive federated intelligence system to diverse and personalized needs. The second one is on-device adaptability, and including agent personalization and allowing multimodal data for collaboration training. And it focused on how to adapt federated intelligence to different tasks and different domain. And the last one is on-device choice, privacy and explainability, and including the privacy, security, and explainability with multi-agent collaboration. Let's take a look at the basic agent architecture. And first, the user send a request to the central agent, and the central agent act like a dispatcher, and directing the request to various sub-agent in the cloud. Just like the agent divided a complex task into different simple subtasks. And this sub-agent handle different tasks like using tools and storing memory and making plans. And once each sub-agent completes its job, and the results are combined into one clear and unified response. And finally, the central agent sends its response back to the user. But we know because large language model agents are quite large, and they are usually hosted in the clouds, and they also allow us to assist them through API calling instead of deployment locally. So sometimes we need to handle local time or personalized task, and relying cloud-based agents can feel a bit reached. So the challenge is that deploying this agent locally is not easy, and due to issues like limited computational resource and privacy concerns and the potential latency. This page shows the on-device agent deployments, the challenge of on-device agent deployment and its potential solution. Just like some sort of language models such as Llama with size up 400 billion parameters, and are too large and computationally intensive for some resource limited device like our cell phone and some edge sensors. So they make real-time and on-device AI application challenging. So we have we summarize two key techniques to make this model deployable. The first one is knowledge distillation, and the second one is quantization. So for KD, the knowledge distillation, and it transform a large, powerful teacher model and to a smaller student model, and widely used in large language model like DeepSeek is used KD techniques to distill some information from ChatGPT. And the quantization is to remove unnecessary weights to compress the data format, such as converting 32 bits weights to 8 bits, and which reduce storage and computational requirements without significantly affecting the final performance. So although we have this potential solution for the deployments, there are always a trade-off between reducing model size and maintaining performance. So slowing and achieving a right balance among these two items is critical for real-world application. For the challenge of communication efficiency, we have a simple figure to illustrate this challenge. In the federated intelligence system, and the agent like agent 1, 2, 3 send frequent updates to a central server, and which aggregated them into a global model or global cohesive response. But this frequent communication consumes significant bandwidth and increased latency and drives up cost. So this problem that are especially critical in some resource limited application, like some healthcare and international of IoT. So the question is, how can we reduce communication overhead while maintaining high learning performance? So addressing this challenge can make federated intelligence system faster and more efficient and more practical. So this slide show a potential solution for communication efficiency in federated intelligence, and which combine agent pooling and knowledge distillation, which aims to reduce the communication overhead and while retaining the essential capabilities of the system. And the first step of the framework is pooling is to estimate the importance of each component, and this involves analyzing which embedding and or attention head or channels are contributing most significantly to the model performance. So by ranking these components based on their importance, and we can identify some importance and less critical elements. So next, the system moved to pruning, and where the less important components are just away and layer by layer. So, and we know if we perform pruning on large language model or language-based agents, the model size will be reduced, but the performance will also be reduced. So to ensure the small model retain its performance, and we can use the knowledge distillation to retain its performance, like the illustration of our last slide. And it set teacher model and the student model, and encourage the teacher model transfer the knowledge to the student model. And another solution for communication efficiency is specification updating, which reduce communication overhead and while maintaining model performance. Like the figure, traditional dense activations in large language model involves every input activity or neurals in the network, and resulting in a high communication cost, especially in federated setup where updates must be exchanged frequently between clients and the server. So to address this, DRU introduced a mechanism where only sparse subsets of neural is activated for each input. So by using these DRU techniques, the federated intelligence system can decrease the bandwidth requirement and enabling more efficient and scalable communication between multiple distributed nodes. And another solution is MOE, just mixture of expert-based updating. And the core idea of MOE is to divide the model into multiple specific components, and we call it experts, and use a router to dynamically select only the most relevant and most important expert for a given input. And this can significantly reduce communication overhead while maintaining the performance. And on the right, we compare the dense MOE with sparse MOE, and in the dense MOE setup, and all neural network, all feed-forward neural network are activated for every input and result in high computational demands. In the right of the figure, and sparse MOE actives only the most relevant feed-forward neural network and are determined by the router based on a gating mechanism. And this means only essential information is processed and communicated, and cutting down in overhead. This slide shows the challenge of agent personalization, and like the figure, and the multiple agents interact with the private data and tasks, and each agent need to be personalized for its specific use case, while also benefiting from the global knowledge shared across in the collaboration system. So how does this framework works? And the first step is agent perform multi-agent updated, and where they train locally on private data without sharing it. And on the next step, and these updates are aggregated on a central server to create a generative model or generative outputs that capture global patterns. And finally, the aggregated model is then sent back to the agents, and who refine it to better suit for their local task, and creating personalized solution for each user and or each agent. So key question is, how can we develop personalized agents that work effectively with private data and the task without compromising privacy? And the second question is, how do we balance global generation knowledge that benefit from all agents, and with the local personalizations that specific optimizations for each agent? So this page show potential solution for the challenge of agent personalization, and it used the prefix turning to activate the activate the agent for agent personalization capabilities. The key idea in prefix turning is to go beyond the input embeddings, instead of adding the soft prompts that maybe contains lots of different trainable parameters. Prefix turning attach it to each transformer block and in the model. And this modification allows us to allows the model to learn task-specific adjustments at a deeper level, and influencing not just the input layer, but all layers of the transformer architecture. And this slide show a different parameter efficient fine-tuning strategy for agent personalization. And in prefix turning, as we just seen, and the trainable prefix are prepended to the input embedding, and but differences in the adapter method is that introduce adapter layer into each transformer block, and this adapter and another way to solve the challenge of agent personalization is llama adapter. It reintroduces a zero initialized attention mechanism coupled with gating mechanism. And the motivation behind this is zero int attention and gating is that adapters and prefix turning could potentially disrupt the sequence knowledge of the pre-trained large language model agents by incorporating randomly initialized tensor or parameters, and resulting in unstable fine-tuning and high lost value during training process. And the base goal of the llama adapter is related to prefix turning, and there are some additional and subtitle difference in how difference in the implementation. And for example, only a self-attention inputs key and value sequence are modified via the trainable soft prompts. And then depending on gating mechanism and the prefix modified attention is either used or not. And this concept can help us achieve and more efficient large language model based agent turning, and we can maintaining the trainable parameters on each client or each user, and to achieve user specific or client specific personalization. And this slide shows the challenge of aligning multimodal data for collaborative turning. This setting is different agents handle diverse data types, and for example, a text agent process documents, and vision agent works with image or videos, and speech agent handles audio data. So the challenge is this data often different in structure and formats, and even domain-specific biases, and making it difficult to aligned and integrating them. So the goal is to combine the output of these agents through effective alignment and aggregation, and creating a unified multimodal solution for a multi-agent system. Such a model could treat complex tasks like generating videos and documents or audio outputs. So to achieve this, we have three key questions need to answer. And the first one is, how can we effectively align multimodal data from text, image, and audio and other different data sources across different agents? And the second one is, how do we address format and domain bias without sacrificing accuracy? And the last one is, how can we ensure robust collaboration while preserving both data privacy and agent specialization? So this page provided a potential solution for the aforementioned challenges. The process begins with complementary local training on individual clients, and where image clients and the text client learn their respective representation, and this representation are aligned through shared embeddings and gates, and ensure that information from one modality complements to other. And for clients with both the image and text data, multimodal local training used both the modalities to learn unified representation from these two different models, and with an alignment loss that ensures consistency between image and text feature. This page show challenges of privacy security in federated intelligence. Like in this slide, we show the agent 1 and the agent 2 sharing updates with the central server, while the protect raw data and it open a door to potential risk. Molecules agent could inject harmful or biased updates into the global response or global model, compromising its integrity. So the consequence of such attacks are important, and an inaccurate global model can lend a harmful output, specifically in critical areas like healthcare and some finance. So there are systems where trust, safety, and precision are absolutely non-negotiable. So for the challenge, we have two questions need to answer. The first one is how to ensure privacy of data while enabling secure collaboration across different agents. And the second one is how to defend against the molecules agent and adversarial attacks in the federated learning, federated intelligence system. So for the potential challenge, for the potential solution, we have differential privacy. Is a privacy preserving techniques that to add some random noise in raw data or raw updates from different agents or different clients. And finally, like the figure and consider a data set of 500 records, and which each record contributed to a collective analysis. And we used the differential privacy calculated amount of noise is added to the data during processing. And this ensures that even if one record is removed, reducing the data set to the 499 records, and the model's output remains almost identical. So this can achieve privacy preserving federated intelligence framework, and without compromising some performance. And the last one challenge is explainability with multi-agent collaboration. And in a collaborative system, multiple agents work together to process cross-domain data, and their output are combined into a unified model. But for some end user like doctors and policy makers, and understanding how decision made is critical to establishing trust in this system. So for the challenge, we have three questions need to answer. The first one is how to interpret model decision across diverse agents. And the second question is how to address domain-specific bias introduced by private data. And the third one is how to provide the human understandable explanation for predictions or outputs. So this slide show a simple and potential solution for explainability within the framework. And the three agents work together, and in these slides, we can decomp this agent's decision to provide the explainability. Like the figure, the floor plan for three agents have sophisticated planning, and from the perspective of explainability, we can divide the complex planning into three different but simple planning. And from the decomposition, we can understand the decision making and the region of decision making step by step. And it is a practical step toward addressing the explainability challenge in multi-agent collaboration system. So that's all of my presentation, and thanks for listening. Anyone have a question about these contents?